Welcome back to part 3 of chapter 3, Energy in the Ecosystem. This is where we left off, so we'll slide to the next one. And also talking about ecosystem productivity. This is just looking at sun's energy here. And notice 1% of solar energy is actually captured through photosynthesis. So basically the sun's energy, photosynthesis, is basically 1% efficient. So 99% of the solar energy is then reflected, and producers don't pick it up. That, when I first learned that, was astounding to me. I just figured it would be more efficient, and that I didn't realize there was so much sun there that it wouldn't. Basically what you're looking at here, there's two sets of initials, Gpp and Npp. Gpp is gross primary productivity. Gross primary productivity is the amount of photosynthesis that takes place and the amount of biomass, then, if you will, that's stored in the plant that can be passed on. Plants tend to respire just like people do cellular respiration, and although they don't do it as fast as we do. So actually what you're seeing here is a 60% loss, and 40% then goes into that plant from the sun. So it's actually gaining more energy. There's not as much heat loss, but there's still some. So your net primary productivity is the amount of biomass that is available to that first level consumer. And that's usually around 40% of the gross productivity. Okay, this equation you might need to know. So it's gross primary productivity minus cellular respiration gives us net primary productivity, which is the amount of biomass that is available for the consumer, the primary consumer. And if you get a problem like this, it'll either be a subtraction problem or an addition problem. They will either give you gross and cellular respiration, or they'll give you cellular respiration and net, and you'll have to find gross. So either or. It's either a positive or plus or minus. Looking at this just so you get an idea of what ecosystems are the most productive and the least, you're going to copy down algal beds and reefs, tropical rainforests, swamps and marshes, and then for the least, you're going to copy down oceans, deserts, and extreme desert. Algal beds and reefs have lots of photosynthetic ability going on. Lots of algae. In reefs, we're talking about coral reefs, and there's the zooxanthellae that actually has the mutualistic relationship with the coral. So coral reefs have to be in the sunlight and have very clean water. Algal beds, areas of algal growth or algae, and obviously if you've got an algal bed, it's very thick with algae, so you have lots of productivity going on. Tropical rainforest, not only does it have very, very high biodiversity, but it has an enormous amount of productivity. And then second comes in our swamps and marshes. This is going to be like the Everglades, because you have a wet environment that's damp with water that is very shallow, sets it up for lots of algal growth as well. And then when we see the ocean, in close to the shore, you're going to have algal growth, you're going to have lots of seaweed, but you've got to realize how vast that ocean is. So when we get out into the middle of the ocean, the water is really moving fast, and while there's some seaweed and some algae that grows, there's got to be some phytoplankton. It's not a high percentage. It's not very dense at that point, and so that's why we say the ocean has some of the least primary productivity. Tripping over my words tonight. Okay, human impact on net primary productivity. We represent 0.5%, 0.5% of the biomass, but we use 32% of the net primary productivity. So what does this mean? Once again, we looked at developed nations a couple of days ago in class and how they used most of the resources. Well, this is the human race altogether, and we're a fraction of a percent of biomass, but yet we're using 32% of it. Could this lead to species loss? Could it lead to extinction of species? Absolutely. Absolutely. If they have no habitat, some of them are going to die. There's got to be habitat. When's the tipping point? There again, I come back to that. When's the tipping point? When the planet can't support human and non-human inhabitants. If it can't support both, if it supports humans, it will not support us if we lose the non-human inhabitants. We've got to have them. This is the case study on the Antarctic food web. We're going to go over this in class, so I'm not going to spend a huge amount of time here on it, and I do want you to read it. It was part of your reading that you need to be doing. Basically, a lot of things going on in the Antarctic food web. What this is showing, if you look at this food web, krill feeds on phytoplankton. Krill is like a little teeny shrimp. And basically, look at all the food interactions just in this one that it shows. It's showing going to baleen whales. Baleen whales eat thousands of pounds of krill, squid, and fish. And there's other things that eat the krill as well. But look what eats the squid and fish. So if we take the krill out of this, what happens to the food web? It could collapse. This is called a keystone species. It's a species that holds a higher rank, if you will. Not on top of the food chain necessarily, but it has more influence on the food chain than another organism would have. If we lost the seals in this food chain, it doesn't really necessarily show that there would be an issue so much. The toothed whales are eating seals, but they're also eating penguins, and they're also eating fish, and they're also eating squid. So not as much of an issue. But pull out the krill, and the food chain comes tumbling down. So this is a keystone species. Things that are playing, this is the little krill right here. Things that are causing problems in this Antarctic food web. Things that are affecting the number of krill there. Loss of the ozone layer. Okay, many of you talked about pollution causing the ozone layer to the loss of the ozone layer. Well, it is a kind of pollution, but not from carbon. These are chlorofluorocarbons that, not from carbon dioxide emissions, but they're chlorofluorocarbons. And that is from aerosol. It's a propellant and a refrigerant that we used to use. We don't use anymore. But it put a hole in the ozone, which is up in the stratosphere. And that ozone actually acted as a filter for UVB rays. And UVB rays are the reason that you now use sunscreen every time you go outside. They can damage your skin and cause cancer. Well, they're finding that in the DNA of the algae, there's some mutation. And mutation in DNA can cause the algae not to reproduce correctly. Algae are the food for the krill. So if the algae aren't reproducing at a high enough rate, then the krill numbers are going to dwindle because there's not enough food for them. Another thing, global warming. That average global temperature is going up, which reduces ice pack. We already talked about the polar bears. And the algae actually colonize close to the ice. And so that also affects the growth of the algae, not having that ice to kind of, if you will, cuddle up to. Therefore, krill don't have as much algae to eat. Another thing wreaking havoc on this system is aquaculture industries or fish farms. And they're actually harvesting the krill and for food for their fish. So it's a free source of food for them. And so if they're taking it, then the natural ecosystem is losing krill. So the less krill there are, the less whales there are going to be, the less seals there are going to be, and I'm just going to flip back again so you can see this. The less squid, the less fish. This is a big deal for the Antarctic food web. And once again, this is human impact, loss of ozone, global warming, and aquatic fish farms. Our other case study, Life Without the Sun. This is just showing a different ecosystem. The Galapagos Rift off of Ecuador is 8,000 feet deep. And that's what this picture is of right here. And these are tube worms. These are actually organisms. And they are down in the depths, very close to these hydrothermal vents. Now, these hydrothermal vents are very, very hot. They're called smokers. And it looks like what's coming out of them is a deep, dark smoke. In essence, it's got hydrogen sulfide gas coming out of these, very hot. But the bacteria down there, instead of using sunlight for photosynthesis, bacteria are the producers. And they use the hydrogen sulfide in order to make organic compounds and to live, and then organisms like the tube worm will filter feed and eat the bacteria. So that starts that food chain. I'm going to see here, I haven't ever done this before, but that's the end of our show, end of our chapter. I'll see you for chapter 4.